By now, I'm hoping that you've looked at the in-class activities, and that should give you an idea of what the structure of the proof that the real numbers are uncountable is going to be like. So in this video, we're going to put the finishing details on that proof. We're first going to review lemmas from the in-class activities. We're going to state the theorem to remind us what it is that we're proving. We're going to review how we set up the proof by contradiction, what we're assuming, what it is that we're trying to contradict. And then we're going to prove the theorem. So recall the most important lemma, but also kind of the easiest to prove, was the following. If you let a be a real number that's less than b, and let x be in the closed interval between a and b, then we can find a closed interval j that is contained in the closed interval between a and b, such that x is not in j. We proved that one in class. I'm not going to go ahead and try to prove that one again. So here is the big lemma that helped us construct those intervals to exclude the outputs of our function. We're going to let in be the closed interval between the real number an and the real number bn for n greater than or equal to 1 be a sequence of closed intervals. So in this case, you always have to have an less than bn for it to be an interval, such that an plus 1, bn plus 1 is contained in the closed interval an, bn for all n. So each interval is contained in the one that comes before it. Then we have the following results. First of all, if we have n less than k, then each ik is contained in in. So it's not just each one is contained in the one that came before it. Each one is included in all the ones that came before it. And that is just an easy induction. I'm not going to prove that one in this video. Again, if n is less than k, then we have an less than or equal to ak less than bk. The ak less than bk is just by definition, and then bk is less than or equal to bn. And that actually follows from 1. In order for ik to be contained in in, the left endpoints have to be to the right of the left endpoints of in, and the right endpoints of ik have to be to the left of the endpoints of in. If we look at the set A of all the left endpoints of the closed intervals, and we let B be the set of all the right endpoints of the closed intervals, those sets are bounded. They're all bounded below by A1, and they're bounded above by B1. All you do is look at number 2, let n equal 1, and it just follows from that. Now 4 is the one that's going to be hard to prove. This is one we're actually going to prove in this video, so let's pay attention. A is bounded above, so it has a supremum. We'll call that alpha. The set B is bounded below, so it has an infimum. We'll call that number beta. And then we can prove that alpha is less than or equal to beta. That's what we're going to prove in this video. And then the 5th one, once we have alpha is less than or equal to beta, each alpha, the interval between alpha and beta is a subset of the interval between each an, bn. And again, I say interval between alpha and beta. If alpha is equal to beta, it's not technically an interval, but I'm going to call it one. Call it an abusive terminology. Leave a nasty comment down below. That's fine. However you want it, that's what we're going to have. All right, and so this follows from the fact that each an is less than or equal to alpha. Alpha is less than or equal to beta from number 4, which we're going to prove, and then each beta is less than or equal to bn. All right, so we're going to prove that alpha is less than or equal to beta, and we're going to do it by contradiction. So we're going to assume that alpha is bigger than beta, and we're going to prove a contradiction. So remember, alpha is the supremum of A, and what that means is 2 things. First of all, it is an upper bound for the set A, but it also means that if you take any number that's smaller than alpha, that one's not going to be an upper bound. And if you look at the line up there, I see a number that we're assuming is smaller than alpha, and that is beta. We know alpha is greater than beta, or we're assuming it. That means that beta is not an upper bound of A. And what does it mean to not be an upper bound of A? That means there's an element of A that's bigger than beta. So beta is less than one of the AKs. at least one of them. Now, we know that beta is equal to the infimum of b, and that also means two things. First of all, it's a lower bound for the set b, but also if you take any number bigger than beta, that one is not going to be a lower bound. And if you look a line up, there's a number that's bigger than beta. That's ak. So, beta is less than ak. That means ak is not a lower bound for b, which means that ak is bigger than one of the bn's. Not necessarily bk, but one of them. We don't know. It could be a big one, it could be a small one. It doesn't matter. It's bigger than one of them. Well, that turns out to be an issue because it turns out that all the AKs are less than all the BNs, but we're going to have to prove that. So I'm getting a little ahead of myself. So we're going to have to do it in two cases because otherwise it's going to be a big old mess. But if n is less than or equal to k, then we know the relationship between the bn and bk, an and ak. That'll make it easier for us to handle things. So we know that bk is less than or equal to bn. That was from one of our results from the previous slide. We know that bn is less than ak. That's just what we got in the line above. And we know that ak, and so that we put those two inequalities together, that tells us that bk is less than ak, and that contradicts the fact that ak has to be less than bk. Remember, ak is the left endpoint of the interval, bk is the right endpoint of that same interval. We can't have the right endpoint be less than the left endpoint. And we're going to get a similar contradiction if we assume that k is less than or equal to n. Here we're going to start with the fact that bn is less than ak. Again, that's just from two lines up. ak is less than or equal to an. That's from one of the results that we had from the previous slide. And that tells us that bn is less than an. And again, same contradiction as we got above. The right endpoint can't be less than the left endpoint. Contradiction. All right, so now that we have those lemmas, now we're ready for the main theorem, which is to prove that the set of real numbers is uncountable. So for our assumption for contradiction, we're going to assume that it is countable. Prove a contradiction. That means there exists some function from the natural numbers to the real numbers that is one-to-one and onto. We're going to focus on the onto part. So we're going to prove that f cannot possibly be onto. That's our contradiction. And what that also means is that there is some element in the real numbers that's not in the range of f. So we're going to take the range of f, we're going to try to avoid it, find a bunch of numbers that don't hit any of the elements in the range. So we're going to define the intervals in recursively as follows. So the first one's going to look a little funny, but it makes sense. We've looked at this before. I1 is the interval with the left endpoint f1 minus 2 and right endpoint f of 1 minus 1. If that looks weird, all we're doing is we're taking an interval to the left of f of 1. The whole interval is to the left of f of 1, so we don't include f of 1 in that interval. If you wanted to do f of 1 plus 1 and then fm plus 2, that would give you an interval on the right side of f of 1. I don't care which one it is. We're just choosing an interval that doesn't include f of 1. f of 1 is not an I1. Then we're defining this recursively, so we can now assume that we've defined in for n greater than or equal to 1, and we just have to explain how to get in plus 1 from that. Well, it's not going to be too hard. From the first lemma, there exists an interval j in that closed interval in that does not contain f of n plus 1. Right? So the idea is in has avoided f of 1 through f of n, and now we want to create a new interval that also does not include f of n plus 1, and that's j. And we can do that from that very first lemma that I had on this video. And then we're going to let in plus 1 be that j. Right, so that gives us a recursive definition of all of our intervals. And we got a claim that we have to prove before we get to the very end, and that is for all the n's greater than or equal to 1, f of k is not an in for all k less than or equal to n. Now we constructed in so that it doesn't include f of n, right? But not only does it not contain f of n, it doesn't contain f of any of the other previous ones. So we're going to prove this by induction. So we're going to start with the base case. We start with n equals 1. By the way we constructed I1, f of 1 is not in it. So that takes care of our base case. For the induction step, the induction hypothesis says that we're going to assume that f of k is not in In for all k less than or equal to n. And we're going to show that f of k is not in In plus 1 for all k less than or equal to n plus 1. All right, so we know that In plus 1 is contained in In. That means that it can't contain any of the f of k's where k is less than or equal to n. If it did, that same thing would also be in In, which we're assuming did not happen by our induction hypothesis. So all we have to do now is show that f of n plus 1 is not in In plus 1, but that is based upon how we defined it, right? We defined In plus 1 to be an interval that did not contain f of n plus 1, so that's not in it either, and that completes the claim. So if we let In be the closed interval between an and bn, so that we're defining what an and bn are. Those are the left and right endpoints of our In. We're going to define a to be all the left endpoints of the intervals. We're going to define b to be all the right endpoints of the intervals. We're going to let alpha e be the supremum of a. Remember, the a's increase as the subscripts get bigger. Alpha is going to be the supremum of all those. The betas get smaller as the subscripts increase. We're going to let beta be the infimum of b. So, first thing we're going to do is prove that alpha is less than or equal to b. We don't have to prove that. We proved that in a previous lemma. I'm being silly right now. Alpha is less than or equal to b. We did prove it. I'm not going to prove it again. That means that the interval between alpha and beta is non-empty. That's really important. We also know that the closed interval between alpha and beta is contained in each of the a and b n's for all n. We proved that in the lemma as well. Now our claim is that none of the f of n's are in the closed interval alpha beta, right? None of the outputs of our function can possibly be in that closed interval. Well, we know that for each n, that f of n is not in the interval between an and bn. We also know that since alpha is bigger than an and beta is less than bn, that the interval alpha beta is contained in the interval between an and bn. That means f of n cannot be in the closed interval between alpha and beta. If it was, then it would have to also be in the interval between an and bn. And so, done with the claim, but the claim gives us everything, right? We know that the closed interval between alpha and beta is non-empty and does not include any of the range, and that means that f is not onto. It does not have as outputs the numbers between alpha and beta. That's our contradiction, and that finishes off our proof.